In Chapter 4, we'll cover probability. In the first section of Chapter 4, we'll learn some basic concepts of probability. Rolling dice, finding parking spaces, winning at cards, these are all some situations where you might want to know the odds of an event happening. If you want to know how to find probability, you first have to figure out what kind of question you have. Some probabilities are easy to identify, like the probability of getting a certain number on the roll of the dice, or the probability of picking a red card from a deck of cards. The single most important objective of this section is to learn how to interpret probability values, which are expressed as values between 0 and 1. A small probability, such as 0.001, corresponds to an event that rarely occurs. A large probability, such as 0.95, corresponds to an event that is almost certain to occur. Another concept of this section is how the odds of an event relate to probabilities. Odds are commonly used in situations such as lotteries and gambling. Probability plays a central role in the important statistical method of hypothesis testing. We will learn more about hypothesis testing later on in this book. Statisticians make decisions using data by rejecting explanations such as a chance based on low probabilities. In probability, we deal with procedures that produce outcomes. Some important concepts with probabilities include an event, which is a collection of results or outcomes of a procedure. A simple event, which is an outcome or an event that cannot be broken down any further into simpler components. And a sample space. This is the procedure that consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. Let's consider the following example of simple events and sample space. In this example, we will consider two procedures. The first procedure, we will consider a single birth, and for the second procedure, we will consider 3 births. We will use a B to denote a baby boy and a G to denote a baby girl. We can say that a single birth is a procedure. With one birth, the result of a girl would be a simple event. As well, the result of a boy would be another simple event. These are individual simple events because they cannot be broken down any further. For this example, let's say the result of the birth would be a girl. The sample space of this event would be all possible outcomes of gender. So our sample space for a single birth would be a boy or a girl. And we will denote this with a curly bracket B, comma, G, curly bracket. Let's consider the procedure of 3 births. If the outcome of this procedure is 2 boys followed by a girl, the simple event would be B, B, G. If the outcome is a boy followed by a girl followed by another boy, the simple event would be B, G, B. If the outcome is a girl followed by 2 boys, then the simple event is G, B, B. If we make a general statement of having 2 boys and a girl without indicating any order, then we do not have a simple event. This is because it can occur in 3 different simple events. We could have a boy, boy, girl, or a boy, girl, boy, or a girl, boy, boy. With 3 births, our sample space consists of 8 different simple events listed in the table. We could have 3 boys, 2 boys followed by a girl, a boy, a girl, a boy, a girl followed by 2 boys, or finally we could have 3 girls. Let's review some notation for probabilities. A capital P denotes a probability. A, B, C would denote some specific event. So if we say P, open parentheses, A, close parentheses, this denotes the probability of event A occurring. When finding probabilities, the possible values will be from 0 to 1, where a probability of 0 would be an impossible outcome, and 1 would be a certain outcome of an event. The probability 0.5 would be an event that is as equally likely to occur as it is likely to not occur, such as getting tails on the toss of a coin. We can denote the probability of an event occurring as 0 is less than P parentheses A close parentheses is less than 1. Let's consider the following three approaches for finding probabilities that result in values between 0 and 1. In an experiment or survey, relative frequency of an event is the number of times the event occurs divided by the total number of trials. In relative frequency approximation of probability, we can conduct or observe a procedure and count the number of times that event A occurs. We can denote relative frequency approximation of probability as P open parentheses A close parentheses equals to the number of times A occurs divided by the number of times the procedure is repeated. For example, if you observe 100 cars passing by and you found that 23 of them were red, the relative frequency approximation of probability would be 23 divided by 100. Classical probability is the statistical concept that measures the likelihood of an event happening. It also means that every statistical experiment will contain elements that are equally likely to occur. The typical example of classical probability would be the fair roll of the dice, because it is equally probable that you will land on any one of the 6 numbers of the die. If a procedure has n different simple events that are equally likely, and the event A can occur in s different ways, then we can write the probability of A as simply the number of ways A can occur divided by the number of different simple events. And we would denote this as S over n. Subjective probability is where you use your opinion to find probabilities. For example, you may think you have an 80% chance that your friend will call you today because her car broke down yesterday and she'll probably need a ride. Or you could think you have a 50-50 chance of getting a job that you applied for because the other applicant is also very qualified. So a more formal definition of subjective probability is the probability of an event A is estimated by the knowledge of the relevant circumstances. Sometimes none of the preceding approaches can be used. A simulation of a procedure is a process that behaves in the same way as the procedure itself so that similar results are produced. Probabilities can sometimes be found using a simulation. A simulation is a recreation of a real-world process in a controlled environment. An example of a simulation would be to see how many times heads comes up when you flip a coin 50 times. When expressing the value of a probability, either give the exact fraction or decimal, or round off the decimal results to 3 significant digits. When the probability is not a simple fraction such as 2/3 or 5/9, we can express it as a decimal so that the number can be better understood. The law of large numbers shows us that if you take an unpredictable experiment and repeat it enough times, you'll end up with an average. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. Some cautions to consider regarding the law of large numbers. The law of large number applies to behaviors over a large number of trials, and it does not apply to any one individual outcome. Also, if we know nothing about the likelihood of different possible outcomes, we should not assume that they are equally likely. The actual probability depends on factors such as the amount of preparation and the difficulty of the test. Let's work through an example of finding the probability of dying when making a skydiving jump. In a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in deaths. We can use the relative frequency approach to find the probability of a skydiving death as follows. The probability of a skydiving death would equal to the number of skydiving deaths divided by the total number of skydiving jumps. That would be 21 divided by 3 million, which is a very small number, 0.000007. In this example, the classical approach could not be used because the two outcomes, dying or surviving, are not equally likely to occur. A subjective probability could be estimated in the absence of any historical data. Let's consider another example. In a study of U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving during the same time period. Based on these results, if a high school driver is randomly selected, let's find the probability that he or she texted while driving during the previous 30 days. A common mistake is to blindly plug in numbers and get the wrong probability. For example, the probability of this event happening is not equal to 3,785 divided by 4,720. Instead of trying to determine an answer directly from our given statement, first summarize the information in a format that allows clear understanding. This format is 3,785 texted while driving plus 4,720 did not text while driving. This gives us a total of 8,505 drivers in our sample. We now have all of the information we need to calculate our probability. We can use the relative frequency approach to calculate this probability. We can say that the probability of texting while driving is equal to the number of drivers who texted while driving divided by the number of drivers in our sample. This gives us 3,785 divided by 8,505, or a probability of 0.445. Be careful when you're thinking about the numbers involved and what they represent when you're calculating your probabilities. So what does this number tell us? It tells us that there is a 0.0445 probability that if a high school driver is randomly selected, he or she would have texted while driving in the previous 30 days. Complementary events happen when there are only two outcomes, like getting a job or not getting a job. In other words, the complement of event A happening is the exact opposite of that event. In statistics, we say that the complement of event A, denoted by A bar, consists of all outcomes in which event A does not occur. Let's go back to our skydiving example. Remember that we knew that in a recent year there were 3 million skydiving jumps and 21 of those jumps resulted in death. Recall that we found the probability of dying when making a skydiving jump was 0.000007. Now let's find the probability of not dying when making a skydiving jump. Among the 3 million jumps, there were 21 deaths. So it follows that the other 2,999,979 jumps were survived. So we get the probability of not dying when skydiving is equal to 2,999,979 divided by 3 million, which gives us a probability of 0.999993. Note that if you add up the probability of dying when making a skydiving jump and the probability of not dying when making a skydiving jump, the sum would equal to 1. This is because dying or not dying would be all possible outcomes when skydiving. If, under a given assumption, the probability of a particular observed event is very small, and the observed event occurs less significantly than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. This is known as the rare event rule for inferential statistics. The basic idea here is that we test a claim by distinguishing between two different things. 1, we have an event that occurs by chance, or 2, we have an event that is highly unlikely to occur by chance. If a highly unlikely event occurs, then we explain this by stating that a rare event really did take place, or that the assumption we started with is not true. For example, if you flip a coin 10 times and you observe 10 heads and 0 tails, would you believe that this is a normal balanced coin? Or would you have any doubt and have that coin tested to see if it is a fair coin? We use probabilities to determine when results are significantly high or significantly low. X successes among N trials is a significantly high number of successes if the probability of X or more successes is unlikely, with a probability of 0.05 or less. X successes among N trials is a significantly low number of successes if the probability of X or fewer successes is unlikely, with a probability of 0.05 or less. A quick review of probability. The probability of an event is a fraction or decimal number between 0 and 1 inclusive. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. We use the notation P open parentheses A close parentheses is equal to the probability of event A occurring. The notation P open parentheses A bar close parentheses is the probability of event A not occurring. Expressions of likelihood are often given as odds. For example, someone might say the odds of an event are 50 to 1. Odds make it easier to deal with money transfers associated with gambling. Probabilities make calculations easier, so they tend to be used by statisticians, mathematicians, and scientists. Let's look at two types of odds. The actual odds of event A occurring is the ratio of the probability of A not occurring divided by the probability of A occurring, usually expressed in the form of A to B, where A and B are integers. We can reduce the odds using the largest common factor. So, for example, if A equals to 16 and B equals to 4, then we can express the odds as 4 to 1 instead of 16 to 4. The actual odds in favor of event A occurring is the ratio the probability of A occurring divided by the probability of A not occurring. This is the reciprocal of the actual odds against that event. If the odds against an event are A to B, then the odds in favor of the event are B to A. Another type of odds are the payoff odds. The payoff odds against event A occurring is the ratio of the net profit, if you win, to the amount you bet. In other words, the payoff odds against event A is equal to the net profit to the amount you bet. If you bet $5 on the number 13 in the roulette wheel, your probability of winning is 1 over 38. But the payoff odds are given by the casino as 35 to 1. Let's find the actual odds against the outcome of hitting a 13. Then we'll find how much net profit you make if you win by betting $5 on 13. And finally, if the casino was not operating for profit and the payoff odds were changed to match the actual odds against 13, how much would you win if the outcome was 13? Let's find the actual odds against the outcome of hitting a 13 on the roulette wheel. We know the probability of getting the number 13 on the roulette wheel is 1 over 38. Therefore, we can conclude that the probability of not getting the number 13 is 37 over 38. From this, we can calculate the actual odds against getting 13 as the actual odds against 13 is equal to the probability of not 13 divided by the probability of 13. This is equal to 37 over 38 over 1 divided by 38. This can be reduced to 37 over 1, and we would write this as 37 to 1. So the odds against hitting a 13 is 37 to 1. How much profit would you make if you win by betting $5 on 13? We know that the casino payoff odds against 13 are 35 to 1. And so we have 35 to 1 odds are the net profit to the amount bet. So there is a $35 profit for each dollar you bet. For a $5 bet, the net profit is $175 because 5 times 35 is equal to 175. The winning bettor would collect $175 plus the original $5 bet. After winning, the total amount collected would be $180 for a net profit of $175. How much money would you win if the casino was not operating for a profit and the payout odds were changed to match the actual odds? If the casino were not operating for a profit, the payoff odds would be changed to 37 to 1, which is the actual odds of hitting a 13 on the roulette wheel. With payoff odds of 37 to 1, there would be a net profit of $37 for each dollar bet. So a bet of $5, the net profit would be $185 for the bettor. The casino makes its profit by paying only $175 to the gambler instead of the $185 that would be paid if the roulette wheel were fair instead of favoring the casino. This is the end of Chapter 4, Section 1. Please proceed to Chapter 4, Section 2.